Welcome, my dear students, my beloved sons and daughters. All of you are most welcome to your favorite YouTube channel, Saraswati Shama, which all of you know is an educational channel guiding the budding degree and diploma engineers in their pursuits of technical knowledge. My dear sons and daughters, today we will discuss four characteristics of a thermodynamic system, process, path and cycle. That is, what is meant by a thermodynamic state, I will discuss. What is meant by a process, the definition will be given, and what is meant by a path, thermodynamic path, that will also be defined, and what is a cycle, that will be defined. And with these definitions and the descriptions, I will discuss about the Carnot cycle, and I will deduce in a very simple form the efficiency of the Carnot cycle. Before I discuss the Carnot cycle, let us see what does the word state or the process or the path or the cycle mean. You see, my dear sons and daughters, a thermodynamic state is the condition of a system defined by properties like, you see, pressure, temperature, volume, you may say the internal energy, the entropy, enthalpy, etc. The thermodynamic state is pointed by its properties, or you may say the characteristics or the qualities. Now comes process. A process is the change from one state to another, and the path is defined to be the exact series of intermediate states. That means when a body, or you may say the working fluid, pass through a several states to reach a final state, then the set of states through which the thermodynamic system goes at a time is called to be the path. A cycle is a sequence of processes returning the system to its initial state. The cycle means, suppose I want to go to market from my house, which is 1 kilometer away. Now, I will follow a path to reach the market, and I will come back through either the same path or a different path. There may be so many paths from my house to reach the market. Someone is shortcut, someone is longer. Now, when I go to the market, complete the work in the market, and again return to the house, the operation that we do, that means the paths we follow, or I follow, completes the cycle. That means where from I started, I again return to that point after going through several places, and this is called the cycle. I give you an example. Suppose a process is isothermal expansion. a gas is expanded isothermally, then it is isothermally compressed. Compression is opposite to the expansion. The gas is expanded isothermally, it reaches a particular point or state, and therefrom it is compressed, it is another path, and it again comes back to the original state. Here you find a cycle above. You see in the adjacent picture, there is the cycle showing several processes. The processes are done on or done by working substance contained within a boundary. That means some substance, gas or liquid, is contained within a boundary, the boundary of a system, and the external surroundings is called the surrounding to that substance. And here you will find several processes are shown in the temperature entropy diagram. Let us now first of all talk about the Carnot cycle. Carnot cycle is a very simple cycle. To understand Carnot cycle is easier than other cycles. It consists of 4 processes. Number 1, isothermal expansion, that I was talking. Number 2, adiabatic expansion. Number 3, isothermal compression. And number 4, adiabatic compression. Here, isothermal expansion means during this process, the working fluid expands by absorption of heat. If you add some heat to a thermodynamic system, that means a gas or a liquid, the property of a gas or liquid, even the solid also, that it expands, its volume expands. It is called volumetric expansion. So, in the isothermal process, we add heat to a system consisting of a gas. The gas expands due to absorption of heat. The expansion involves increase of volume and the temperature of the working fluid increases. Suppose the temperature of the gas was at small t. The heat is given to this gas and its temperature becomes capital T. Okay. So, this is an isothermal expansion. That means after the expansion, the temperature, when expansion is completed, so long there will be heat transfer, the expansion goes on increasing, and when the expansion stops, the heat transfer stops, you will find the surrounding temperature and the temperature of the gas is same. So it is called isothermal expansion. That means the temperature has become same. The temperature change causes the change in internal energy. During the isothermal expansion, the internal energy also changes. And if this change in internal energy is found, then it will be seen that initially the internal energy was delta 1, and after the isothermal expansion process, the internal energy has become delta 2. And the change in the internal energy is delta 2 minus delta 1. Now, from the surrounding atmosphere, heat passes to the substance across the boundary, that is in the isothermal expansion process. The heat passes to the substance across the boundary, hence heat addition takes place. This is called isothermal expansion process. Next, the working substance is adiabatically expanded. What is adiabatically expanded? The gas itself expands, but there is no heat or work or any kind of energy transfer across the boundary of the system. The working substance is adiabatically expanded when the substance does some work at the expense of internal energy, but no heat or energy of any form crosses the boundary. The boundary is a barrier to the passage of or transfer of heat or any kind of energy. Here in the adiabatic, it is called adiabatic means there is no heat transfer across or any work, energy or work transfer across the boundary. It is called adiabatic process, and it is the adiabatic expansion process. When the working fluid is compressed isothermally, the heat is transferred to the surroundings across the boundary. That means when after adiabatic expansion, here the temperature drops because the internal energy is expended to do the work. The working fluid is doing a work at the expense of internal energy because there is no heat transfer across the boundary. And as the internal energy is expended, that means the internal energy from delta 2 to delta 3 drops. That is, the internal energy has changed from higher value to the lower value. So, the temperature of the gas or the working substance drops to suppose T dash. And here at the T dash temperature, the isothermal compression takes place. And this process maintains at the same temperature. That means the heat energy is generated due to compression of the working fluid at a temperature higher than T dash. But initially we found when adiabatic expansion completed, we reached the temperature of the system to T dash. That means the surrounding at the temperature when the adiabatic expansion was completed, the surrounding temperature was T dash, with which there was an equilibrium. Now some compression is done and the heat energy is generated. It may be discussed or it may be explained from the molecular theory. I will discuss them in our coming videos. Now I just tell you, when there is a compression, some heat is generated. Now this heat is passed to the isothermal compression. That means there is a passage of heat from the working substance to the surroundings. Surrounding is at T1 or T dash temperature. So how much lower the temperature will come down? That is the T dash temperature of the substance or the working fluid, because below this temperature it will not come down. Why it will not come down below the T dash temperature? That is also a question that will be discussed later on when I will talk about the first law of thermodynamics, second law of thermodynamics, etc. I will tell you that it is not possible for a working substance by itself go down below the temperature of the surroundings. The moment there will be temperature equal to the surrounding, there will be no heat transfer. And without this heat transfer, it cannot go beyond the temperature than the temperature of the surrounding. Okay? That I will discuss when I will discuss about the first law and the second law of thermodynamics. Now, the isothermal compression, you may say, has taken place at a temperature T dash, and the gas becomes very near to its initial state. The working substance has come to the initial state, very near to the initial state. Suppose this is the point 4. Initially started at point 1, after isothermal expansion went to point 2, after adiabatic expansion went to point 3, after isothermal compression it has come to point 4, and from point 4 adiabatic compression takes place. In this compression process, no heat or any other energy crosses the boundary. Here temperature increases to initial temperature. Here, once there is compression, there is work done, but no heat transfer is there. Where from the amount of heat will come to provide this work? The working fluid expands, is compressed, and the work is done within itself, just like in the isothermal compression. When the compression was there, the work is done on the gas. Mind that, my dear sons and daughters, when there is compression, it is done, the work is done on the gas. And when there is expansion, adiabatic expansion, the gas itself did the work. Mind that. This is different. Gas itself does work, and there the fall of temperature. And when there is work done on the gas, there is temperature rise. But the amount of work done that is done on the gas is converted obviously into the heat energy. And this energy could not be transferred to the external atmosphere. So what will it do? It will increase the internal energy of the gas. And this rise in internal energy will be reflected in the rise of temperature. And this temperature, that means the maximum temperature rise will be equal to the original temperature of the substance. Now, here temperature increases to initial temperature. Suppose the system is comprised of a cylinder with a piston attached in one end and the other end closed. The piston can move in and out. My dear sons and daughters, here in the piston connected cylinder, a gas, that is working fluid, is contained. Let us think that we add heat to the gas and piston moves outward and volume increases with temperature rise. And while being heat conductor, heat enters the cylinder to raise the temperature to the value, say, capital T. And after this expansion, an adiabatic expansion takes place. That means gas expands by itself without any heat or energy crossing the boundary. That means I was talking about adiabatic expansion. Adiabatic expansion takes place here. The gas does work by itself and there is a fall in temperature. The initial temperature was T, and suppose the temperature falls to T dash. And the piston moves further and temperature drops to T dash. Next, an isothermal compression, I was talking about isothermal compression, is done by the piston. Now the piston now compresses the gas. Isothermal means there is heat transfer across the boundary. some work is done on the gas where generated heat, work is done on the gas, this work immediately transforms into equivalent amount of heat and this goes out of the cylinder because this is an isothermal process. Isothermal process is nothing but this is the expansion or compression process with the passage of heat energy either towards the gas or from the gas. And the temperature of the gas is maintained the same as the temperature of the surrounding. When it takes heat from heat source, its temperature rises to the temperature value of heat source. When it throws heat energy into the heat sink, its lowering of temperature, the lowering of temperature of the working fluid reaches the value of temperature of the sink. This heat is transferred to the surroundings and temperature maintained at T dash. The compression raises temperature but heat exchange lowers the temperature to T dash. Compression is done at T dash temperature. It is called because the temperature is maintained at T dash after the completion of the compression. The next adiabatic compression is done by pressing piston and this process restores original state of the gas. This process of adiabatic compression raises temperature of the gas because heat does not go out. Because in a adiabatic process there is no heat transfer, work transfer or any energy transfer across the boundary. The heat remains within the substance. Within this substance, the heat is increasing the internal energy. Internal energy is directly proportional to the heat content. When its heat content is increased, its internal energy will increase. And with this internal energy increase or vice versa, the heat energy is increasing the temperature and hence the internal energy increases. To these points I will come in the coming videos. Now this temperature rise is equal to its initial temperature and the process is completed and the cycle is completed after the adiabatic completion and the mass of the gas has come to the original state. These four processes constitute the reversible Carnot cycle. Suppose the amount of heat entering the system is Q during isothermal expansion process. The amount of heat leaving the system during isothermal compression is Q dash. And the work done by the cycle is W. That means this cycle will do some work. I told you the gas is doing work, the compression is taking place, there is adiabatic compression and so on, isothermal expansion. So some amount of work is done by the cycle. What do we mean by the cycle? Different states the gas is passing through and in passing through different states, suppose you go to South India, then you go to Western India, then you go to Kashmir, then you go to you see in Arunachal Pradesh and then again come back to your house. The more and more you travel throughout the country, the more and more work you will do. There will be more and more processes, the work done should be more and more. And hence, the amount of heat leaving the system during isothermal compression is taken to be Q dash. And the work done by the cycle is W, equivalent obviously to Q minus Q dash. Why? Because there is no creation of energy, no destruction of energy. You have given heat. It is an energy to the substance or the working fluid, that is Q. And when you are leaving this energy, that is Q dash, into the sink, so the difference of these two energies, these two heat amounts, Q1 minus Q dash, where did it go? This is nothing but the amount of work done by the working fluid or the system of the thermodynamics. So, efficiency of the cycle. You know, the work done comes from the difference of the heat. One coming into the working fluid, one leaving the working fluid. Their difference is the work done. We are not taking into account the friction, the resistance, and these things actually. Now, efficiency of the cycle given by eta is equal to W. This work done is called the output. I tell you, when boiler produces steam, the steam is the working fluid for the turbine. In the turbine, what happens? The heat energy is transformed into the kinetic energy. And here, the kinetic energy is the output for the turbine. Ultimately, this work done is converted into electrical energy. That is another question. Now, W is the output, Q is the input, because this amount of heat was initially given to the substance, working fluid. Now, in place of W, let me write Q minus Q dash, and then it is divided by Q. This is marked the relation 1. We know that heat is expressed through the temperature. Suppose the amount of heat is obviously proportional to its temperature. This is we all know. Now, we may write from this very basic axiomatic understanding, that is Q is the amount of heat is equal to some constant C into temperature T. Hence, Q dash is equal to CT dash. Regarding these things, I will discuss afterward. I am very simply talking about the efficiency, reducing the efficiency of a Carnot cycle. I am not going deep into the complicacy related with this. I will come to them in coming videos. Now, efficiency eta is equal to T minus T dash by T, because efficiency was Q minus Q dash by Q. Then what happens? T minus T dash by T is equal to 1 minus T dash by T. You make a division here and you will reach the expression 1 minus T dash by T. Multiply with 100 and get the percentage. So the efficiency, I tell you one problem, you yourself find a turbine is running where steam is entering at temperature 300 degrees Celsius. A turbine is designed in this way, and the steam is condensed to the water. That means the T2 temperature is say 50 degrees Celsius. Then, my dear sons and daughters, find the efficiency of the turbine. I give you hints. You yourself do the problem and tell me the result. 300 is the input temperature. The input heat has got the temperature of steam 300. So T is equal to 300 degrees Celsius. And the heat remained in the, you see, in the sink, that is in the hot oil, is say temperature is 50 degree. that is T2 or T dash is equal to 50 degrees Celsius. Then what will be the efficiency of the turbine? Very simple. You solve it yourself and tell me the result. Now, my dear sons and daughters, I finish here my today's discussion. I have taken much time to tax upon your concentration. Thank you for giving me a patient hearing during this video, during this discussion. And those things which have not yet been discussed will be discussed in the coming videos. And my dear sons and daughters, before I finish the discussion, make an earnest request to you that do not forget to press like button, subscription button for those who are new viewer, and the share button so that I may reach as many pupils as it is possible. And for that I hope you are doing well. Goodbye, my sons and daughters. Stay blessed always and be happy today and always remain so. Thank you, my dear sons and daughters. Thank you.